In the previous lecture, we have started to deal with the problem of symmetry operations in crystals or lattice. In the first part of this lecture, we have seen two basic symmetry operations, and those were translation and rotation. Among these, you know, rotation is a point symmetry operation. Okay. Now, today our aim is to deal with the other symmetry operations. As you have learnt in the previous lecture, there are four basic symmetry operations, which are translation, rotation, reflection, and inversion. Since we have already discussed translation and rotation in first part of this lecture, so today we will see the remaining symmetry operations. And in this regard, first of all, we will discuss the two basic symmetry operations, which are reflection and inversion. And apart from that, you have also seen that by the combination of the basic symmetry operations, we get some new allied symmetry operations, among which three are very important, which are rotation inversion symmetry, askew symmetry, and glide symmetry. So today we will learn about all the remaining symmetry operations in present lecture. Okay. So now let us first of all see what is this reflection symmetry. Actually, a lattice is said to possess a reflection symmetry if there exists a plane or a line in case of two dimensions in the lattice, which divides it into two identical halves which are mirror images of each other. It means reflection symmetry. When you say reflection symmetry, what does it mean? It means in case of a three-dimensional lattice, there will be a plane, and that plane will divide the lattice into two identical parts. The two parts just appears as mirror images. It means if you consider that plane just as a plane mirror, then and one of the part of the lattice as an object, then its second part will be just equivalent to its image. For example, you can see this figure. In fact, in this figure I have shown a nosed wheel, and this nosed wheel possesses reflection symmetry. About this line of reflection symmetry, you can see this line which I have drawn here. This is called line of reflection symmetry, and you can see the part of the wheel in the right side of this line of symmetry, and in left side just appears mirror images. So this figure actually illustrates the reflection symmetry of a nosed wheel. Nosed wheel. Okay. Now, mathematically, if you want to define this reflection symmetry, how you can define? Actually, in a mathematical way, a reflection symmetry is expressed by a coordinate transformation. It is represented by a coordinate transformation. For example, you can see, if we consider that the mirror symmetry is about this YZ plane, you can see, or you can consider that this YZ plane represents just a plane mirror, let us say. Okay? And we consider a point P here, as you can see in the figure. And the coordinates of this point P are X, Y, and Z. Okay? Then the image of this P in this plane mirror will be formed at P dashed, and what will be the location, or how the location of this image will be specified? You know that Y and Z coordinate will remain same, but this X coordinate, or since x-axis is just perpendicular to this yz plane, so if this distance is equal to x, okay, then this distance will be also equal to x. But since it is in negative side, so that will be represented by minus x. So you can say that the mirror symmetry about the yz plane can be represented by this coordinate transformation equation: y dashed equal to y, z dashed equal to z, but x dashed equal to minus x. So if the reflection symmetry is just a yz plane, then the coordinate transformation will be like this. There will be no change in y and z coordinate, but the sign of x coordinate will be just inverted. Okay? In a similar manner, if you consider the reflection symmetry about the xy plane, then you can see, if you consider a point here again P and its coordinates are x, y, z, then in this case this z axis will be perpendicular to this plane. And so the image of this will be just at a point whose coordinates will be x, y and minus z. So if the reflection symmetry is an xy plane, then the coordinate transformation will be like this: x dashed equal to x, y dashed equal to y, but z dashed equal to minus z. Okay? So this is all about the reflection symmetry, and you can see, in fact, in this case we talk about the point symmetry. So reflection symmetry is also an example of a point symmetry, as you have seen in the case of rotation symmetry. Rotation symmetry also a point symmetry, and this reflection symmetry is also an example of point symmetry. Okay? Now we will see the fourth basic symmetry operation, which is called inversion. Actually, as you have seen in case of reflection symmetry, that this symmetry is possessed by the crystal in 2 dimension and 3 dimension too. In case of the 3-dimensional crystal, the reflection symmetry is a plane, but in case of a 2-dimensional crystal, then the reflection symmetry is a line. As you can see here, I have considered yz plane and xy plane as plane of symmetry. These will be the reflection symmetry in case of what? In case of a 3-dimensional crystal. But when you talk about the reflection symmetry of a notched wheel, then you can see the line of reflection symmetry has been shown here. Here there is no plane of reflection symmetry, but there is a line of reflection symmetry. So this is this line of reflection symmetry will be in case of a 2-dimensional lattice or a plane lattice. So you can say that reflection symmetry exists both in case of 2-dimensional lattice and 3-dimensional lattice. But on the other hand, when you talk about the inversion symmetry, that symmetry exists only in case of 3-dimensional lattice, not in case of 2-dimensional lattice. So I have mentioned it here. You can see that inversion is a point operation which is applicable to 3-dimensional lattices only. Only in case of 3-dimensional lattice, this symmetry operation, inversion, will be carried out. Okay? Now we will see what is this when we say inversion symmetry operation, what does it mean? Actually, a crystal is said to possess a center of inversion if it is left invariant by the operation r changes to minus r. What does it mean? It means, let us say, if there is a lattice point whose position vector is given by r. Okay? Now, if the position vector r is changed to minus r, let us say this is minus r, that is r becomes minus r. After becoming r to minus r, if the crystal remains invariant or the environment of the crystal remains invariant, then we say that the crystal has inversion symmetry. So you can see I have mentioned it here that a crystal is said to possess center of inversion if it is left invariant by the operation r to minus r. That is, for each point located at r relative to a lattice point, there exists an identical point minus r. Then you can say that the crystal has inversion symmetry. Okay. Actually, symbolically, this inversion symmetry is represented by the symbol I over bar. Writing the sign of bar over I, we denote this symmetry operation symbolically. Okay. And in a mathematical way, actually inversion symmetry is described by the coordinate transformation. It means if the coordinate of a point are x, y, z, then after inversion symmetry, those coordinates will be transformed to minus x, minus y and minus z. It means the new, after this inversion symmetry, the coordinates will become x prime equal to minus x, y prime equal to minus y and z prime equal to minus z. Okay. So I hope you have understood what is this inversion symmetry. So till now we have discussed the four basic symmetry operations. In first part of the lecture you have seen the two basic symmetry operations. First one was translation, another was rotation. And in this lecture you have learned till now two basic symmetry operations, that those are reflection and inversion. Both are point symmetry operation. Now we will see the three allied symmetry operations which are actually resulted by the combination of the basic symmetry operations. And in this regard, the first one is rotation inversion symmetry operation. Rotation inversion. As the name implies, you can see this rotation inversion will be definitely a combination of the rotation and inversion symmetry operation. So we define it that if a rotation followed by inversion about a lattice point leaves the crystal structure invariant, then it is said to possess a new symmetry element which is called rotation inversion axis. Okay. So if you want to perform this symmetry operation on a lattice, first of all you have to perform the rotation operation, and after that in a successive manner you have to perform the inversion operation on the same lattice. Then you will see that if the crystal structure does not change, it remains invariant, then we say that the crystal on which this operation has been performed, that possesses rotation inversion symmetry. Okay. Now regarding this rotation inversion symmetry, we will learn some important facts. First of all, you can see that a crystal can have only 1, 2, 3, 4 and 6-fold rotation inversion axis, and these rotation axes are denoted by 1 over bar, 2 bar, 3 bar, 4 bar and 6 bar. As you have learnt in the previous lecture that a crystal does not have 5-fold rotation symmetry. In a similar manner, you can say that a crystal cannot have 5-fold rotation inversion axis. because it does not possess five-fold rotation symmetry. Only the rotational symmetry which is possessed by a crystal is either one or two-fold, three-fold, four-fold, and six-fold. And so you can say when we will actually combine the inversion symmetry with rotation, and as five-fold rotation does not exist, so the five-fold rotation inversion symmetry axis will also does not exist. And so you can say that a crystal can have only 1, 2, 3, 4 and 6-fold rotation inversion axes, and these axes, as I have told you, are denoted by 1 bar, 2 bar, 3 bar, 4 bar and 6 bar. Okay. Now, another important fact regarding this rotation inversion axis is what? This is a two-fold rotation inversion axis is just equivalent to a mirror plane. So, we symbolically can write that 2 bar is equivalent to M. Here 2 bar means two-fold rotation inversion symmetry, and M means this is a reflection plane. Okay. So as this fact says, a two-fold rotation inversion axis is equivalent to mirror plane. So symbolically we write that 2 bar is equal to M. Okay. The third important fact regarding this rotation inversion symmetry is a six-fold rotation inversion axis is equivalent to three-fold rotation axis plus a mirror plane. It means when you will carry a six-fold rotation inversion axis, the result will be same as if there will be a three-fold rotation axis and after that we consider a reflection. So you can say symbolically that 6 bar is equivalent to 3 plus M. This 3 actually represents the threefold rotation axis, and M represents the mirror plane. Okay. So these were some important facts. You should remember it. All these facts you should mention in the answer of your question, and these facts are also very important for solving the objective type of questions. Okay. Now the second allied symmetry operation is called screw operation. Actually, definitely you have seen a screw in your practical life. You also called it nut bolt. When you open an screw or closed an screw, what happens? You know, in this case, the screw rotates on an axis, XL, and also translate. So in this word screw implies that this symmetry operation is just a combination of rotation and translation. The name says, you can imagine in your mind an screw, as I can show it here. This is just an screw, you know, and this is this screw will move along this let us say x direction, and it also rotate. So this is just a combination of rotation and translation. So if the symmetry operation rotation is combined with the translational symmetry operation, then a new symmetry operation is generated, and we say that our crystal possesses a screw symmetry. Okay. So in a mathematical way, you can say that rotation plus translation is equal to a screw. Okay. I think we have understand what is this SQ operation. Now the third allied symmetry operation is called glide. What is this glide? Actually this glide is the combination of reflection and translation. Reflection and translation. So I have mentioned it here in a mathematical way that reflection plus translation is equal to glide. It means if you want to perform this symmetry operation, first of all you have to follow the reflection symmetry, and after reflection you have to perform the translation. So we simply define that reflection followed by a translation is called glide operation. So in this way we have learned about the 7 symmetry operations, among which you have seen that the basic operations were 4 and 3 are allied symmetry operations. Actually this symmetry operation plays a vital role when we will learn about the Bravais lattice, when we will learn about the classification of lattice. Okay. So I hope you have definitely enjoyed these 2 lectures on lattice on the symmetry operation of lattice, and definitely you should watch the video seriously, write down these things in your notebook, and that will be a very good notes for your examination purpose. Thank you very much.